here's your warm-up. Please pause and solve. Okay. For this first integral, why did you decide that this would still be an improper integral? I don't see infinity anywhere. What's improper about this? Well, if you look at the lower limit of integration, I am integrating from 0 to 1. And what is happening to this function when x is equal to 0? It is undefined. It is actually blowing up. So I cannot, in a straightforward way, integrate from 0 to 1 because this function does not exist at x equals 0. This is an improper integral, and this is the type of improper integral that we're going to learn about today. For the second question, what did you get for this limit? I'm hoping we got infinity. We can think of this one in terms of n behavior. The power in the numerator is greater than the power in the denominator. I can think about the n behavior of this as this minus 2 not really mattering, and this leaves me with x, and as x goes to infinity, this limit will go to infinity. Okay, so today we are going to be learning about the second type of improper integrals, which have to do with those infinite discontinuities. So in order to integrate a function, we know that the function itself has to be continuous, okay? Even when we were integrating all the way to infinity, we still needed that condition of continuity. However, we are now going to learn how to integrate over these discontinuities using, again, the concept of limits. Limits are not going away. This is also called an improper integral. I'm going to call this the second kind. The first kind was the kind where we integrated to infinity or integrated from negative infinity. This kind, we are going to be integrating either from or over infinite discontinuities. Okay, so in this type of improper integral, there is an infinite discontinuity at one of the limits of integration or somewhere between the two limits of integration. For example, the integral I had in my warm-up. 0 is a problem here because this function itself is not defined for x equals 0. Our basic idea is still the same. We are going to replace the problem with a limit that approaches that problem. For example, if f is continuous on the interval from a to b, notice my function is continuous when x is equal to a, but b is not included in this interval. So I have an infinite discontinuity at x equals b. If that is the case, that means b is the problem. I'm going to replace b with a limit as c approaches b from the left of the integral from a to c of that function. Okay? So I'm replacing b in my upper limit of integration with a limit approaching that problem from the left. Okay, because this is my upper limit of integration, we can kind of assume that that x value is to the right, okay, which means as we are approaching it, we're approaching it from the left. These do need to be one-sided limits, okay, because these are often discontinuities, infinite discontinuities that don't match up like this. So approaching that problem from the left and approaching that problem from the right aren't necessarily going to yield the same thing. Okay, let's say my infinite discontinuity is at a instead, is at the lower limit of integration. Same thing. I'm going to replace the integral from a to b of f of x dx with a limit as c approaches that a from the right now of the integral from c to b of f of x dx. This is really similar to what we did with the infinite limits of integration, except we need to worry about what side we're approaching from. These are one-sided limits. Finally, let's say I'm continuous on the entire interval from a to b, including the endpoints, except for some c in the middle. Okay, so let's say I'm integrating, not starting at or finishing at an infinite discontinuity, but I'm integrating over an infinite discontinuity. Then I need to split it, okay? I have the integral from a to b, but I need to split it into an integral from a to that infinite discontinuity, plus an integral from that infinite discontinuity to the other endpoint b. And then I rewrite both of those integrals with the appropriate one-sided limits, okay? So remember, we can't do double limits. So this is going to be the limit as, I don't know, I need a new letter. Let's say d approaches c from the left of the integral from a to d of f of x dx, plus the limit as, I need another letter, let's say e, I don't really like that because e means something, but that's okay, as e approaches c from the right of the integral from e to b of f of x dx. Then I have two integrals, two limits, and really this is going to look very similar to what we were doing with the first type of improper integral. Let's return to our warm-up, okay? So what's the problem? The problem is 0. So I'm going to rewrite this as the limit as, let's call it a approaches 0 from what direction? From the right of the integral of, I don't really like this, I'm going to rewrite this in the numerator as what? X to the negative 1/3 dx. Okay, and I'm integrating from a to 1. I integrate and I evaluate the limit. So when I integrate, I bring my exponent up a power, that becomes x to the 2/3. I divide by that new power and I get 3/2. I need to not forget my limit. A approaches 0 from the right. And this is evaluated from a to 1. So this becomes the limit as a approaches 0 from the right of 3/2 times 1 to the 2/3 minus 3/2 times a to the 2/3. And I've integrated. Now I just need to evaluate the limit. This is equal to what? Just 3/2. And then as a goes to 0, this has no problem, okay? When I integrated, I went from having basically an x in the denominator to having an x in the numerator. Having 0, x equals 0 in the numerator is no issue whatsoever. 0 to the 2/3 is 0. This term drops off and I'm left with 3/2. Okay? I want you to appreciate what we just did. 1 over x to the 1/3 power. Okay, so 1 over the cube root of x still looks pretty similar to this family of functions that we've been looking at. And what I just did is I integrated that from 0 to 1. So I didn't integrate out to infinity like we did last week, but I did integrate kind of up to infinity, right? And so I have this infinitely large region, but I got a finite answer to my integral. I hope your mind is still blown by this. This is very cool. All right, here's another one, the integral from 0 to 2 of dx over x cubed. I want you to try this one on your own, so please pause. Okay, when I rewrite this, I get the limit as a approaches 0 from the right of the integral from a to 2 of x to the negative 3 dx. You with me? So I have now the limit as a approaches 0 from the right. I bring this up a power, which brings it to the negative 2, and I divide by that power, which is going to give me negative 1/2 out front, and this is evaluated from a to 2. So this yields the limit as a approaches 0 from the right of negative 1 over 2 times 2 squared. I moved that back into the denominator, minus negative 1 over 2 times a squared. Okay. This first guy is no problem. This gives me -1/8. But as a approaches 0 from the right, what happens to this guy? It is blowing up. This is going to infinity. So what is the answer to my question? The answer is that this integral diverges. Okay? One last example. I want you to pay careful attention to this one. So pause the video and solve. All right, I hope you realize that even though my limits of integration are both okay, I cross over an infinite discontinuity. This is asking me to integrate over 0, which is a problem because this function is discontinuous there. So the very first thing I have to do is rewrite this as the integral from -1 to 0 of x to the -3 dx plus the integral from 0 to 2 of x to the -3 dx. Okay? Now, I believe we just solved one of these. 0 to 2. Oops. Sorry, guys. Well, we just solved one of these. And found that this one diverged. And if you recall, we talked about this last week, if one of the pieces diverges, then the entire thing diverges. I don't even need to go any further with this. If you did, good for you. But I don't even need to go any further with this because I know that this piece diverges, the entire thing diverges. Okay, so this one is divergent. Now, what would have happened in the previous example if you didn't notice this discontinuity? Sight unseen, I can integrate this, okay? I would get -1/2 x to the -2, evaluated from -1 to 2, which would give me -1 over 2 times 2 squared minus -1 over 2 times -1 squared. And that would give me -1/8 plus 1/2. And that seems like a nice finite answer. Okay, that is an answer for suckers because you have to realize that if I'm integrating over this infinite discontinuity, okay, I get into some trouble. All right, so you have to pay attention to your limits of integration because they will try to trick you with this. We're going to have to be a lot more aware than we were last year because this is not an AB topic, but it is a BC topic. So this issue wouldn't have come up last year, whereas it very much can and will this year. All right, in the last section when we dealt with improper integrals going to infinity, we learned a few different tests for making our lives easier. And those tests apply here. We can modify our p-integral test to include this type of discontinuity. And so I'm hoping you noticed that when we integrated, for example, this guy, he converged, whereas when we integrated this guy, he diverged. If this had been an integral from 1 to infinity, what would this have done? It would have diverged. And if this had been an integral from 1 to infinity or from 2 to infinity, it would have converged. It appears that the relationship reverses when I have this other type of issue, when instead of going to infinity, I'm starting at 0 in the denominator. And that is the case, okay? So I have a new p-integral test. Let me clear this out so that the writing goes away. I have this new p-integral test that basically reverses the order or reverses the relationship of that power. So remember, I always have the integral of dx over x to some power. That's what p-integral stands for, is power. B is going to be some positive number. And this is going to converge if and only if p is less than 1. And it's going to diverge if and only if p is greater than or equal to 1. This is not exactly the reverse of what we learned before, because if p is equal to 1, it still diverges. So the integral from, let's say, 0 to 1 of dx over x is going to diverge. The integral from, let's say, 1 to infinity of dx over x is going to diverge. That's because natural log of x doesn't behave well at 0 or at infinity. Okay, so that power of 1 is always going to diverge, but the others, the relationship reverses. Okay, if the power is less than 1 here, I converge. If it's greater than or equal to 1, I diverge. In addition, the tests that we learned, the direct comparison test and the limit comparison test, still apply. You just need to make sure that you're analyzing the functions over the proper domain. So here's an example. I have the integral from 0 to 1 of sine squared of x dx over the square root of x, and we want to determine if it converges or if it diverges. Okay. I can't remember if we've introduced these trig ideas yet in class. I think we probably have at this point. Sine squared x, we need to think about what multiplying by sine squared x does to this function that I'm integrating. Sine squared of x is going to fall strictly between 0 and 1, 0 and 1 inclusive. Okay, so multiplying by sine squared of x is basically like multiplying by something between 0 and 1, maybe 0, maybe 1, which means that on really any interval, sine squared of x over the square root of x is going to be less than or equal to 1 over the square root of x, which is what I can compare it to. Okay? Now the integral from 0 to 2 of dx over the square root of x is going to do what? It's going to converge because the power in the denominator is 1/2, which is less than 1. So, since this is less than or equal to a known convergent p integral, then by direct comparison, we know that this will converge as well. So I can say that this will converge by direct comparison to this integral, which is a known convergent p integral. Okay, because we are probably running out of time at this point, I'm just going to run through the next few examples without you guys pausing, because each one kind of has a separate trick that I don't necessarily want you guys to spend a bunch of time trying to figure out on your own right now. Sorry. So for this one, okay, if you remember when in class when we were talking about U substitution and I reminded you about Uing your limits of integration and I told you that would come back and be important, this is where it's important. So let me show you. With this one, I'm not sure exactly what's going on. Okay, I'm bigger on the bottom, therefore smaller in total than 1 over x cubed, but when 0 is the problem, 1 over x cubed diverges, so I'm smaller than something that's divergent. I'm not really sure what I want to do with limit comparison. I want to show you a cool trick. If I were actually integrating this, I would rewrite u as x plus 3, and du is just dx. So this would change to the integral of du over u cubed, yes? Then u your limits of integration. U of negative 3 gives me negative 3 plus 3, which is 0, 0. U of 0 gives me 0 plus 3, which is 3, 3. Now I don't need to use direct comparison or limit comparison. This is directly a p integral, okay? And what is p? It's 3, which is greater than or equal to 1. So this is going to diverge. This is just a p integral, okay? I didn't actually compare it to anything. I found something that was identically equivalent to it that I knew diverged, okay? So be on the lookout for that trick as well. Okay, and finally, here is an example that has two problems. The lower limit of integration is a problem, and the upper limit of integration is a problem. So I need to split this into two integrals. I'm going to integrate from 0 to something of dx over the square root of x plus x squared, plus I'm going to integrate from that something to infinity of dx over the square root of x plus x squared. And that something doesn't matter. It just needs to be something between 0 and infinity. Go ahead and pick something. I'm going to take a wild guess, and I'm going to say that you picked 72. Did anybody pick 72? That'd be pretty cool. Haha, I'm so funny. Okay, so let's rewrite both of these with limits. I'm going to have the limit as a approaches 0 from the right of the integral from a to 72 of dx over the square root of x plus x squared, plus the limit as b approaches infinity of the integral from 72 to b of dx over the square root of x plus x squared. And then I have both of these to consider, okay? If one of them diverges, I'm done. It's divergent, okay? If they both converge, then I'm convergent. So let's look at this one, okay? I could compare with either of them to the integral of dx over the square root of x, or I could compare to the integral of dx over x squared. With this one, okay, if I'm going from 0 to 72, from 0 to 72, what does this one do? It converges because my p integral rule works in reverse when I'm dealing with 0. So this has a power of 1/2, which is less than 1. This converges. By the same token, this one diverges. Okay? The denominator over this interval is larger than either of these. Therefore, this overall function is smaller in total. Do I want to be smaller than a convergent integral or smaller than a divergent integral? I would like to be smaller than a convergent integral because by direct comparison test, that allows me to conclude convergence, okay? So I'm going to compare this integral to this known convergent p integral and conclude that this piece converges, okay? For this piece, I have my same two options, except I'm not going from 0 to 72, I'm going from 72 to infinity. And I can compare to this one, or I can compare to this one. On this interval, what does this integral do? We're going to infinity. So this one actually diverges going to infinity, and this one converges. Because when I'm going to infinity, I want that power to be strictly greater than 1. This is the convergent one, okay? On this interval, still, the denominator of this guy is larger than either of these. Therefore, the overall function is smaller than either of these. Now I'd like to compare to this guy, because on this interval, this is the convergent one, and I'm less than it. So this is less than a known convergent p integral, okay? So this converges as well. So because both pieces converge, this integral converges. If you are confused, then you're probably doing this right, okay? We're going to practice a lot more. We're going to practice for probably a whole nother class period tomorrow. I'm thinking we'll have a quiz on this on Friday, but between now and the end of the day tomorrow, you should understand this stuff a lot better, especially if you do your homework. So this is homework number 7 for this chapter. Please do this tonight, and then tomorrow we will go over it. We'll do another extra practice worksheet, and then Friday you'll have your quiz. This pretty much takes us to the end of the chapter, but we're going to do a lot more practice before we test.